How do we measure the length of a curved path? While a straight line is easy to calculate using the distance formula, a curve requires a more sophisticated approach. Today, we will use calculus to derive the exact formula for arc length. The core idea is to break the curve into many tiny straight line segments. If the segments are small enough, their total length will closely approximate the actual length of the curve. We call one tiny segment ds. By looking at a single segment as the hypotenuse of a right triangle, we can apply the Pythagorean theorem. The horizontal change is dx, and the vertical change is dy. Therefore, the square of the segment length equals dx squared plus dy squared. Taking the square root of both sides gives us the length of a single infinitesimal segment. This expression is the building block of our derivation, representing a tiny piece of the total arc length along the function. To make this usable for integration, we factor out dx squared from under the radical. This introduces the ratio dy over dx, which we recognize as the derivative of the function with respect to x. When we pull the dx squared out of the square root, it becomes a simple dx. We are left with the square root of 1 plus the derivative squared, all multiplied by dx. This represents the length of one tiny segment. To find the total length, we sum up an infinite number of these tiny segments. In calculus, this infinite sum is represented by the definite integral from our starting point A to our ending point B. This is the arc length formula. It calculates the exact distance along a smooth curve by integrating the square root of 1 plus the square of the function's derivative over the desired interval. Let's apply this to a specific function. We will find the length of f of x equals 2/3 x to the power of 3/2, evaluated from x equals 0 to x equals 3. First, we find the derivative. Using the power rule, the exponents cancel out beautifully, leaving us with the derivative f prime of x equals the square root of x, or x to the 1/2 power. Next, we square the derivative as required by the formula. Squaring the square root of x simply gives us x. This will make our integration process much more straightforward. Now we substitute our values into the arc length formula. We are integrating the square root of 1 plus x, with respect to x, over the interval from 0 to 3. We integrate using the reverse power rule. The antiderivative of 1 plus x to the 1/2 is 2/3 times 1 plus x to the 3/2. Now we just need to evaluate at the boundaries. Plugging in 3 gives us 2/3 times 8, and plugging in 0 gives us 2/3 times 1. Subtracting these results, we find the total arc length is exactly 14/3, or approximately 4.67 units. As we can see on the graph, this numerical value represents the physical distance you would travel if you walked along the path of the curve from the origin to x equals 3. To recap, always start by finding the derivative, square it, add 1, and then perform the integration. This systematic approach works for any function that is continuously differentiable over the chosen interval. Try setting up the integral for x squared from 1 to 2. Since the derivative is 2x, the square is for x squared. The resulting integral is the square root of 1 plus for x squared. Arc length connects geometry and calculus. By summing up infinite hypotenuses of infinitesimal triangles, we can measure the complexity of any smooth curve. Master this derivation to understand the power of integration. Generated by Vision Solve AI.